If you have any question, you can bring it up. Of the lectures that you going to. Under which cells alias are something I don't know things I saw few people they are working for election. I got one student email me going for election. So you go back. You go back. I go back. One you is your customer. Can one you. They go back for election. By the way, next week we got a quiz. Remember? Yes. I think on last week material probably counting and a bit of relation. Any question about on previous material? I don't know, but I got a midterm. Yeah, I just realized I got a midterm evaluation. Yesterday I go and see the midterm evaluation. I saw someone say, career cannot finish on time. I think, yeah, you can't finish your paper on time because even when I do it, also some requirement. So every time I would put out the tutorials earlier so that you can try and see it familiar first. And then if you can't finish on time, that's fine because I will put out the solution that you study. If you can't do it again, the next lecture you are allowed to bring it up and then ask if you don't know how to do it. Yeah. So you don't need to complain, you just like come and approach me. And I also got a office hour. Just email me. Yeah, you are not on your own. Yeah. Mark. Okay, I think more people coming in. We should start now. Okay, let's start. So let's recall some materials from last week. Again. Yeah, again. So recall from last week. So recall from last week, we have the equivalence relation. Okay. So first we have it is a bilinear relation on the set x. It's a bilinear relation from x to x. Okay. Second, it is reflexive. Third, symmetry. Fourth, transitive. Okay. So today when we talk about equivalent relation, you should keep these four properties in mind. So it's relation, It's really reflexive, symmetry, and transitive. Okay. So last week we also look at the example of congruence. Block 7 is an equivalence relation on when? On what set? Congruence mod 7 is a relation on what set? What are the elements you consider? Incongruence mod 7. Incongruence, what's the element you consider? 0. Huh? 0. What? 0 to 6. 0 to 6. I mean, it's a congruence relation on what set? Yeah, integer. Okay, it's on integer. So it's a bilinear uh, it's a binary relation on integer. If you only have then convert to be 1, 7, 4, some and b. Okay. Okay. And we also talk about this congruence partition Z. Right. Remember the picture that if you got Z, they are partitioned by 7 equivalent class. 1, 2, 3, 4, 5, 6, 7. Partition by 7 equivalent class. Meaning every element in Z belong to one of the equivalent class. Okay, so we will make this idea precise today. Okay, so we'll make this idea precise today. So first, let us observe that what does it mean to be an element is equivalent to another element? Okay. So let us start with an equivalence relation. Okay. So the following are equivalent. So what does it mean to be A is equivalent to B? Okay. So you can study about their equivalent class. Okay. It turns out that their equivalent class should be the same. Okay, they're equal, except. But if you look at the intersection, it is non-empty. Okay. So what does it mean to be the followings are equivalent? Okay. So this means 1 will implies 2, 2 will also implies 1, and then 2 implies 3, 3 will implies 2, and then 3 will implies 1 as well. So they form a cycle. Okay. So when two elements are related, okay, actually their equivalent class is the same. And the intersection is non-empty. Okay. So if by contrapositive, if they are not related, then the intersection will be. So this one will be the one we'll be using later. If it is not related, then it is empty. This is the contrapositive. Okay. So let's see why is it true. Okay. So to prove the statement, it suffices to show 1 implies 2, 2 implies 3, and 3 implies 1. Okay. If we can do this, then we will form this cycle. Maybe you will ask about this arrow, right? So this arrow can be achieved by going around. Okay, going around the circle. So it's enough just to show the cycle. Okay. You get the logic here. You get the logic here. So to show this cycle, I can show every arrow here. Okay, there's a logic here going in. Yeah, if any problem, you can just point out. Okay. So we need to show these three arrows now. Okay. So I reduce to showing these three arrows. So let's try to show one implies. Okay. So we want to show that two equivalent class is the same, right? So what is equivalent class? So all the elements they are related to the element, the representative. Okay. So we want to show this. That is to show that A is a subset of B and B is a subset of A. Because A and B, okay, I just recall here. Maybe I recall here. Equivalent class A is equal to the set of B. Okay, maybe use another method C in the element such that A is equivalent. Yeah, maybe use the same equivalence. Okay, so it's a set. So you want to show set equality. Set equality, you need to show the right hand side, the left hand side is the subset of the right hand side, and then the right hand side is the subset of the left hand side. Okay, so you need to show these two set inclusion. So show the first one to see that the right hand side is a subset of the left hand side. The left hand side is a subset of right hand side. Okay. Take an element in the right hand side. Okay. You need to show that it's an element of the right hand side. Okay. Then X is, if X is in the equivalent class of N, that means what? X satisfies this relation here. Okay, X is in here, X satisfies the relation here. So what? So then X, then we have, then we have A is related to X. Okay. So we got A is related to X since we have A is related to X and A is related to B. Again, what can we conclude? Can we conclude anything? Yeah. A is related to X and A is related to B. Can we conclude anything? Can we conclude anything about X and B? X is related to B. Since we have we see that X is related to B. Why? By actually you need to do symmetry sometimes. Symmetry and transitivity on R. Okay, so to write it out here. So if A R X, then X R A, right? Okay, so this is the symmetry part. So if AX is in R, then XA is in R. Okay, this is the symmetry. And then if XA, AB in R, then XB is in R. Okay, so we got SB in R. So SB in R means, hence X is in the equivalent class of R. Okay, because X is related to B, and then so it's in the equivalent class of B. Okay. If you want, you need to solve again, or you change the definition of it. So we have shown that we take any element from the equivalent class of A is the element of equivalent class of B. So we've shown this set inclusion here. So want to show them, okay. So you can try similarly try and prove B is a subset of A. Okay, going through the similar argument here. Okay. Okay, next part 2, second, we want to show 2 implies 3. Yeah. So let's assume the equivalent class is the same, and then we want to show that this intersection is not empty. Okay. So let's suppose okay. So let's so we want to show that the intersection is not empty. Okay. So what is the question is what is the intersection of this A and B? Given that you know the two set is the same, okay, you know the two set is the same, are the same, then what is the intersection? What is A intercept A? A, right? So A intercept B is just either A or B. Go to the equivalent class of A, because these two sets are equal. Okay. So equivalent class of A, why is it non-empty? Can you find some some element inside the set? The equivalent class of A. What are the elements in the set? These are the elements that are equivalent to A. In particular, what element is there? A. Yeah. So we have the intersection is equal to the equivalent class of A, and A is non-empty precisely because A is in the equivalent class, since R is reflexive. Okay, for all A have to be in a relation. So A have to satisfy this relation. So A is in the set. A R A. Okay. Okay. So there's at least one element which is A inside the equivalent class. Okay. Okay. Next, we go 3 to 2. Okay. Now it's 3 to 1. Show 3 to 1. 3, 2, 1. Okay. Assume the intersection is not empty. We want to show that A is related to B. Okay. So suppose the intersection is not empty. Okay. Then we can find and element call it C is in the intersection. Okay. Which means X is in A and C is in A and C is in B. Okay. So when C is in A, we have C is related to A. And if C is in B, we have C is related to B. Okay. So can you say something about A and B? Are they related or not? How? A is related to B by symmetry and transitivity again. Okay, so you can CRA implies ARC, implies ARC, and then ARC CRB implies ARB. Okay. So A is related to B. This is how we want to show. Okay. Yeah. So okay. So really although we talked about partition last week, but we never say the real definition. Okay, let's talk about the definition of partition first. So what do you mean by partition? Okay. So partition, you have a set, and then you consider some disjoint, non-empty subset of your set. Okay. So if you take their union, and then it happens to recover your whole set, then you will call it a partition. Okay. So in set theory wise, how do you write it down? So let's say you have a set of subset, okay, called AI. So these are the subset of your set. And I is just some index set. Okay. So this is called index set. And then this index set is a subset of some natural number, okay, ordered set. Forms partition. Okay, what does this mean? If and only if this AI should be non-empty, okay, for all AI, and then their intersection should be empty for pairwise intersection, and the union of all subset disjoint subset is the original set X. Or sometimes we will write the, okay, never mind. Should I introduce maybe later? Okay. Yeah. Okay. So you got a partition. Okay. So for example, you got a cake. You got a cake. You want to partition it. So when you partition your cake, right? So these two pieces, these four pieces have no intersection, right? Okay. So yeah. So if you partition to A1, A2, A3, A4. Okay. So there are no intersection, and then the union of them is the original. Okay. Original set. Okay. So yeah. Okay. Let's think about how equivalent classes will form a partition. Okay, so the procedure, let's try another experiment. Okay, so procedure. So first we start with a set. Okay, you start with an arbitrary set. Call it X. Okay, you start with a set X, and then you put equivalence relation on it. Equivalence relation of X. Okay, you put equivalence relation on X, then you will like relate elements with elements, right? Okay, so you will form equivalent classes. Equivalent classes for related elements. So in your mind, you should have another list going on in your mind. So in your mind, you should have Z. Okay, we got integers. And then we put equivalent classes congruence mod 7. Okay. And then how many equivalent classes we have here? So we got 7 equivalent classes. Okay. So that means every element in your set belong to some subset. Okay. And then what you need to show is these empty subset are the intersection is empty. Okay. Right. To form a partition, what you need, the union of the disjoint subset is your original set, and then the intersection is empty. Okay. So every element here belongs to some equivalent classes. And then if you want to show the other inclusion, it's easier because all of the AI is the subset of X. So you automatically got this. Okay. So the next thing is to show the pairwise intersection is empty. But by this definition, by this theorem here, if if you have different equivalent classes, okay, not the same, then by contrapositive, this is empty. So by theorem before, if AI is not equal to AJ, then their intersection is empty. Okay. So hence what? Hence the equivalent classes of A, hence the equivalent classes of what? Of the relation of partition the X. Okay. So this one you also can have similar argument here. So this set on partition set. Okay. So let's write down the statement here. So theorem. Suppose you start with equivalent class again. Sorry, equivalent relation. What I see here also got problem. Relation on set X again. Then the equivalent classes of R form a partition of X. Okay. So equivalent classes, so give you an equivalent relation, okay, give you a relation, equivalence relation, you can form partition. Okay. But conversely, you can ask another question. If I give you a partition, can you get me an equivalence relation? Okay. If you're thinking backward, okay, so can you? No? Isn't wrong. Okay. Actually, yes. Okay. So converse is true as well. So if you are given a partition, okay. So if you're given a partition, actually you can form a equivalence relation. Okay. So bear in mind, what is relation really? Okay, in mathematics, what is relation? Okay, relation is not by the definition of relation, it's just a subset of a Cartesian product. Okay, it's just a set of Cartesian product. If I form the ordered pairs, I don't even need to tell you why they are related, how they are related. Okay, it's enough. I just tell you a subset of Cartesian product is enough. So that's why we have this converse here, because it's not, how to say, not strong, not detailed. Yeah, not detail of the original. It's because, yeah. Okay. So so what? Yeah. So let me give you an example. Instead of proving it, I give you an example. If you want to see the proof, you can see inside your textbook. But it's exactly the same argument when I illustrate with this example here. For example, so now we start with a partition. So procedure now is start with a partition of set. Okay. And then give an equivalence relation. Okay. I will illustrate with an example. So let's say we start with a set containing maybe contain 5 elements then. So let's start with 1, 2, 3, 4, 5. Okay, this is my set X. Okay. So what's the partition? So the partition I pick is 1, 2, 3, 4, and 5. Okay, this is my partition. Okay. So now need to form an equivalence relation. Okay. So remember what's the equivalence relation is? A binary relation. Okay, from X to X. And then it's reflexive, it is symmetric, it is transitive. Okay, so 4 of these. So R is a subset of X cross X. Okay, let's form this R then. So let's define R to be first the order pair 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So why do I include this? Because it is reflexive. So for every element in the set, okay, we want 1 is related to 1, 2 is related to 2, 3 is related, okay, and so on. The next one is symmetry. So in this set here, where we put 2, 3, 4 here, that means 2 is related to 3, 3 is related to 4, and 2 is related to 4, right? Okay. But if 2 is 2, 3 is in the set, 3, 2 also need to be in the set so that your relation is symmetry. And then 3, 4 is in the set, 4, 3 has to be in the set. And then if 2, 4 is in the set, 4, 2 is in the set as well. Okay. How about transitive? If 2, 2 in the set, 2, 3 in the set, then 2, 3 is in the set. So 2, 3 is in here. And then 2, 3 is in here, 3, 2 is in here, 2, 2 is in here. Okay. And then if 2, 3 is in here, 3, 4 is in here, 2, 4 is in here. Okay. And then I think I claim that this is the relation. I think I claim that this is the equivalent relation corresponding to the partition. Okay. So give a partition, I give you an equivalent relation. Okay. I don't need to know like what is the relation between the two, but I just need to give you a subset. Okay. Okay. Any question or not? Any question? We're going too fast. Any question?
Relation. It is showing that
relation. Definition of relation. Definition of relation. Okay, so okay, so a relation. Okay, so okay, so let's recall. A relation. Okay, maybe start from the. So an equivalence relation. Okay, is a relation. Okay, maybe not two. Okay, just start from a relation first. A relation on R is a binary relation from from X to X. Okay, so binary. What is a binary relation? The binary relation from X to X is a subset of X posets. Okay. So I just need to give you a subset of X posets. And then what is if you add the adjective here, equivalence relation, that means you need to satisfy reflexive, symmetry, and transitive. Symmetry, reflexive mean for every A is in the relation. So A is in the relation, A is in the relation. Okay. And then symmetry, if AB is in the relation, BA is in the relation. Transitive, if AB, BC in the relation, BC is in the relation. Okay. Yeah. Yeah. Okay. So relation is subset of the Cartesian product. Yeah. Okay. Any question? How about we let me see. How about we stop here and then for rest and then we'll come back. 9:52 we start.应该可以回切啊，这个飞机，对。我本来不想回呢，本来不想回。现在应该涨比较有但涨到好像900多啊，快1000块了。
去一层我再决定300块。对啊。我第一次要换，我把它都，然后我完全不懂，完全没有关注的。我跟你讲哦，是换哪个没有换一样的，没有什么改变的东西还是一样的，还是一样啊，改变的。没有换歌词，没有老师，我跟你讲，他们每次啊要选到的时候啊，就开始重拆了。哎呀，是这样的，然后每次没有做好的，然后别选上我们很多了。他开始选，你就会看见西部那个马路在那，开始哭了。你那边开始猜，我那边是开始哭啊。真的假的？真的开始猜啊！那个你们那边要拿票啊，这样。不是报复性，他也要减速的。没有，他就是没有选上去，他就没有做了，没有做了，他就。不会比较好，放的就不好的。我没有啊，每次教他选的时候，放我的猜。才把你在哪个哪个？你这视频学习是吧？没有啊，其实我不太紧张的。没有多。基本的话就是不让人教，那有可能是属于。对，我先跟就看到一满对对对，这边是就不仅他三个人的，他也没有同等，他也可以高一点。我卷了，都真的是东西马山。但是这样可以出去，轻的话就看到人了，打一天的头牌，然后。还在给放到自己。哎呀，台湾整个比赛你挨个话都打人干嘛呀？啊？这个话都打人，他妈关键时间到了。在练习停电啊！第二天再去工作啊，停电要点自然一点。如何停电？大家这个怀疑，把那个第二点放进去。要讲法庭的，要不是突然间整场。可以下，可以下，没有说，我觉得我讲。哎，讲这个这个有啊，有放出来。不是，我是说像你这种课件的，这里不是有？
这个跟你那个还是有点不一样。你这些例题也没用到。
对，
就只有 definition 可能稍微
啊，对，
是，或者是把这个就是各自讲。然后我觉得那挺好疯了，因为你在上面写，我也就只能，
你就跟吧，
我就只能就是等着，然后容易走神。
容易走神。
就是如果你看上笔出来的话，我一个一个跟着看，可能
我不想翻出来，是因为怕你翻出来过后就不会有人就是
也不会吧？就是我想的是那样效果好一点。
是哦，但是我想要的方法不太一样。但是我怎样说呢？
比如说你在上面写，我在下面，
对，
因为你有笔记嘛，我也做不了这个笔记，然后只能干听着
啊，就听。
但是就很容易走神，因为你有一个东西上面可以勾画啥的，就是像
我建议是你可以，你就听，然后你不明白的话，你可以问。
不是不明白，就是
如果你说要概念什么的，不是，你可以先预读、预习，因为你这些啊，我跟你讲啊，就算他没有答案在这里啊，那些答案也是在你的课本里一模一样。所以课本里面已经有一套完整的东西了，所以你要预习的话，你就预习。啊，因为课本里面所有的答案、习题答案那里，例子有答案。
我想的是，如果笔记放出来的话，然后我可以跟着笔记题，就是你到哪一页，
对，我明白，
我明白。
但是，试下这个学习方法。
就是其实大多数人也就是课上不怎么听，他就是课后看你的笔记，等你笔记发出来再看。比如说期中考试，大家都是课上都下课直接看笔记，那我觉得还不如课上的时候，课上的时候跟着你看。
这样，
我觉得是这样。
你觉得？
因为说到你什么，因为你这个课，因为你笔记都做好了，不需要做什么。
其实我笔记是空的，我给你看，我是临场的。
临场。
你看，我给你看我笔记，我只是大概写我要做什么嘛。
对呀，就是
跟你那个差不多一样。你看我没有铺在这里了，我是临场写，我没有铺在这里了，这是空的，这也是空的。
哎，那可不可以把这个先放出来？是你的，
但是这个跟那个就差不多一样了啊。那个会比我多东西，但是这个跟这个差不多一样的，跟正常的。这个
就是这样的话，
我的脉络跟这个是一样的，只是有时候我会多一点点吧，或者我会少一点点。
就是你的题是不一样的
啊，我题是不一样的，对，我题不一样就是想让你们看更多不一样的东西。这里面已经有的东西，你就这里有的东西，我可以老实跟你说，这些其实就是课本
哦
啊，因为你要找他怎么解释这些啊，就是在那个课本那一段东西就是在讲这些。
就是我想笔记
发一下，
可以跟着这样课上的时候
但是我也是可以老实跟你讲，它是可以，所以我到明天结束过后，我会开始填这些东西进去，因为我要知道你们需要知道什么，有时候我准备的东西，你们像你讲的就不能够接受有些东西，但是补充一些你们比较觉得重要的东西过后，你们就可以接受。对，所以我也没有准备完整的，我是大概有一个骨架我要的。 但是我就是怕像你说你们想要先看嘛，所以我就也放一些隐形，大概脉络是这样，但是
我觉得这个倒是没什么用，因为我只有一些分一偏移，其他
对呀、我也是这样哦，我也是这样哦，
如果你硬要把它后面那个，
我也是这样的。这些 proof 啊，刚才我们写的那些 proof 啊，我是零产错出来的。
就比如说你把这个框架放出来，然后
框架，
我可以直接跟着你做例子，就不用，因为题目大家都没有，然后我也，因为你也后面也有笔记，就可能跟着写一点东西好一点。反正我的想法，
哎，要开始了，呃，我想一下，想一下再跟你讲。什么东西？
哦，我这个是可以的啊，肯定可以，
肯定可以，先放出来，可以先放出来。
就预习了。
呃，
或者是我们今天完了就可以看到了，因为老师你明天还要带团啊，对，就没办法。
啊，可以什么？
可以先放出来，
可以先放出来。
但是吸收更好。
嗯，
有一边抄一边看，
你是说先，他的是说 lecture 前放出来，lecture 前放出来，但是我有放一个 past year 的 lecture notes。
白了，
那个有点不全的感觉，就有的时候你有的会效果会
没有解释了，有个
啊，对，没有，他的解释是在课本里面找得到的。
但是有的时候不知道就是重点在哪里，
啊，对，然后中间会跳掉了。
就有的时候会浪费精力。看一个都不知道讲啥，看来东西我讲那个去。
你讲吧。讲一下。嗯。
投个票，投个票。
OK，来投个票。
62个人承担。
Hello，OK。Okay, your friend suggests I put up a lecture note before the lectures. What do you think?
Yes.
Yes. Yes. No. Okay. The problem with putting out the lecture note before the lecture, I scared like if I put out the lecture, then you won't come. Right. So you can just study yourself. Or you need to come for attendance. No, I mean your attendance later you fake also how? So I don't know. So how? Huh? How? You help me settle the problem, then I help you settle the problem. How? Okay. Because before I set up the course, I know that maybe you have this kind of concern. That's why I put out last year lecture notes so that you at least got something to follow. But even though I put out those lecture notes, actually they are also in the textbook. So if you really want to like want to study first, you should look at the textbook. What if I point out the suggested reading section every week before the lecture? Can. Okay. Because I can let you see my lecture note. I let you see my lecture note. Right. Okay. I think I just use that. I don't need to use. Yeah. I let you see my lecture notes. It's actually empty one. You see, there's no proof here. Just now the proof I write on the spot one. There's no proof here. No proof here. Yeah, nothing. But I mean, because yeah, I don't know. Like I cannot prepare because I don't know. Like depend on your feedback, right? Then I will add more detail or I remove details. Okay, so I just put um the body. I think the body. I put symbol one. Then after I finish tomorrow class, okay, I'll add in all the details that you guys want from 3 classes. Then I combine all the details and then I will revise and then I put up on the Thursday night. That's why sometimes it's late because I need to change something. Yeah. Okay. But I will put out as early as possible. I adjusted my lecture notes. Okay. So if possible, maybe I string down the suggested reading area every week. So it's like based on what I prepare, then I tell you the section, and then you can read the section. I also read this section and then I prepare one. Is it okay? Is it okay? Yeah. Because I cannot give you details also. I don't have details. Okay. Next. Okay, let's continue. Very good. So keep giving me feedback and then we will like make the course better. Okay. And let's see. Okay. So let's continue. Okay, next part is about partial ordering. Okay, previous part we talked about symmetric, transitive, symmetric, reflexive relation, right? Okay. Now we focus on the relation that is anti-symmetric. Okay. So we call a relation a partial ordering or partial order if it is reflexive, anti-symmetric, and transitive. Okay. So we call it so we will denote it by another by XR. Okay. Denoted by XR, which we call it a Poset. Poset or a partially ordered set. Okay. Because this P and O together become Poset, partially ordered set. Okay. Denoted by okay. And then we also denote A is less than equal to B. Okay, so see here the less than equal is a bit weird here. It's not the really less than equal to. It's not the number less than equal to, but we will denote A is less than equal to B if AB is in the relation where R is a poset. Okay. So for example, what are poset? You will have integer where you have greater than equal to. Okay, it's a poset. It's anti-symmetric, right? Because if A greater than equal to B and B greater or equal to A, then A is equal to B. Right? It's a poset. Since if A greater than B. Okay, 2. Divisibility is a poset. Okay. Last time we talked about, right? Because it is antisymmetric. If A divide B, B divides A, that's only when A and B is the same. Okay. What else? We have power set of a set. Okay. If you look at the set inclusion relation, if A is a subset of B and B is a subset of A, then A is equal to B. Right. This is what we have, the relation we had last time. These are all the poset. So inside poset, right, we can compare elements, okay, and also there are elements that are non-comparable. So if there are 2 elements in your poset, okay, are called comparable, if either A can compare to B or B can compare to A, or if they are not comparable, then we will say that they are incomparable. Okay, if you can't compare them, that means they are incomparable. So let's see some example, right? So what's the example? Maybe we look at the divisibility. So example 2. Okay. So for example, 2 is less than 4. Why? Because 2 divide 4. Okay. 3 is less than 9 because 3 divides 9. Okay. But 3 is not less than 4 or 4 is not less than 3. Right? Because neither 3 divide 4. Okay, maybe if I put neither, then no need to say. Oh, okay, maybe don't want neither. Because 3 doesn't divide 4 and 4 doesn't divide 3. Okay. There's something you cannot compare, there's something you can compare and also. Okay. So let's say your poset, if everything you can compare, okay, what happened? Then you will form if you can compare every 2 elements in your set, okay, then X is called a total order. It's called a totally ordered or linearly ordered set. Okay. And the less than relation is called a total order. You can order everything, so totally you can order them. And or sometimes we call it linear order. But that's not important. But you see that a totally ordered set is actually we call a chain. So let's see on this example Z with a less than relation. So with this less than, right? So you can total order your element like this. Fine. Okay. So from the side you can see that This is like a chain. Okay. Like a chain. Is it like a chain? Yeah. Okay. Okay, next. So total order. And then the next one is well ordered. So a set is a well ordered set. If it is a poset such that you have a total order. Okay. And every non-empty subset you have a least element. Okay. Okay, so for example, the natural number is well ordered. Okay. So natural number is what? So for example, we have 0 less than 1 less than 2 3 less than 4 less than 5, then keep going on. Okay, I haven't passed down the. Yeah, okay. So every subset you can consider it contains a least element. Okay. But if you look at Z, then it is not well ordered. Okay, because you got like the chain like going forever small. Okay. So this is not good. Okay. So in summary, we have so in summary, we have one is Poset. Okay. After Poset, we will go to total order set. Okay, we compare compare every two element, and then 3 will go to well ordered. So there's a least element for every non-empty set. Okay. And then the next one is lexicography order. Okay. So what's lexicography order? It's actually the order you use in the dictionary. Okay. So let's give two Poset again. Given two Poset, okay. How do you define the lexicography order? So you need to tell me how two elements in the Cartesian product are comparable. Okay. So let's say we take two elements from the Cartesian product. So when is A1, A2 less than B1, B2? Okay. If and only if A1 is less than equal to B1, or if both A1 equal to B1 and A2 is less than equal to 2. Okay, so just give a clear example, you will see it. So for example, ball is less than star is less than supper. Okay, so ball, why is it less than star? Because if you compare the first one, B come from before X. Okay, and then the second one, If the first one is the same, you check the second one. So lexicography order. Okay. So you can generalize this definition to Cartesian. You can generalize it to Cartesian product of n poset. Okay, A1, A2, A, then keep going. Okay, then you can keep comparing all the numbers behind. Okay. Okay, next. Next, we will talk about Hasse diagram. Will we start with an example? You want to see example first or you want to see construction? Example first. Okay. So let's bring this up then. Okay, let's see example. What's the okay? So Hasse diagram first, you start with a poset. Okay, so start with a poset. Okay, poset. Okay. So you draw arrows for every relation. Okay, there's arrow for every relation. So look at this poset here. Okay, this is the set. This is the partial order. So they have relation if they are less than equal to one another. Okay, so 1 is less than equal to 1. Okay, 2 is less than equal to 2. 3 is less than equal to 3. 4 is less than equal to 4. Okay, and then 1 is less than 2. 2 is less than 3. 3 is less than 4. 2 is less than 3. 1 is less than 4. 1 is less than 3. 2 is less than 4. Okay, so you draw all the arrows. But turns out that some of these arrows are redundant. Okay, because in Poset, we automatically know it is reflexive. Okay, so we can throw all the loops with this path here. We can throw it away. Second, we know that Poset is transitive. Okay, so this arrow we also can throw because if you want to get 1 to 3, you just go from 1 to 2, 2 to 3. Okay, so we can throw this arrow, throw this arrow, throw this arrow. So we're left with this picture here. And then because this arrow got direction, right? So you can arrange from bottom to top, the initial vertex to the terminal one. For the starting arrow until the end. Okay, so we can throw, after you arrange, you can just throw the arrow, the direction. Okay, because we know that this direction is always going up. And then this is the Hasse diagram. Okay, so definition. Okay, after we do this definition, I will let you try one example. So let's spell out the definition. So what's the Hasse diagram of a poset? So first you have a directed graph. So you draw a directed graph by drawing arrows whenever you have a relation. Okay. Arrows from A to B, whenever A is in B. Okay. A and B are related. And then 2, remove all the loops. Okay. Remove all the reflexivity. 3, remove all the edges, the transitive edges, okay, such that there is an element Z in X such that X is less than equal to Z. And Z is less than equal to 1. Okay, remove the transitivity. And then for arrange each edge so that its initial vertex is below terminal vertex. Okay, and then 5, remove all the arrows. Okay. Okay, so let's come back to this example, and then I want you to try and draw out now what is the Hassel diagram for T 1, 2, 3 with the individual. Okay, I give you 3 minutes. Try draw out what is the Hassel diagram for the power set of 1, 2, 3, and then with the relation set included. Okay, try and draw out the Hassel diagram. I give you 3 minutes. And then I will call people to show the diagram. I draw a Hassel diagram for this based on this example. Anyone have done? Has anyone done? Is someone called Ming Hao here? Or not? Ming Hao. Huh? Oh, Ming Hao, you're here. Hey, last week you're not here, right? Why Chung Mai not here today? You guys suck, ah? Huh? What? What, Hector? Huh? Hector. Got answer for the diagram? Got do or not? Huh? Got do? Where? Anything? What's the diagram? Oh, yeah. Oh, okay. Wait. Yeah, okay, I thought I know, I thought you know, so not sure if you are confused with this or not. So the power set of the set is what? Or the set contain 1, 2, 3 is what? Remember the exam question? We got the empty set. 1, 2, 3, and then 1, 2, 2, 3, 1, 3, and 1, 3, 2. Okay, so you need to order this set with set inclusion. Anyone got done do with this set here or not? What name? What name? Eng Sun Chen. Eng Sun Chen here or not? Where, huh? Oh, the guy went to toilet. Okay. Li Wei here or not? Li Wei. Oh, you are Li Wei. Got do or not? Huh? You don't know. Huh? What? On this side, simple version one. Some got change and someone got change and Eric, Eric. Eric here or not? Eric Kun. Eric Kun? Huh? What? Where is he? Huh? Genting Highland. Go vote or go play? Huh? Uncle Lim. Oh, okay. Understand. Okay. Eric. Daniel. Go do?
Not sure.
Go try? See? Okay, so what Daniel did is he arranged this set like this. Okay. He arranged the set like this. Okay. Okay, arrange the set like this. Okay. But you still need arrows. Anyone put arrows down? Oh. Can you explain your answer?
Me?
Yeah, you.
Oh,
How you draw that?
this draw, this one.
You talk. You explain.
Okay, people, pay attention. Like this.
Why draw like that?
Wait. Wait. One. And then. This. Is the arrow? Do I need the arrow?
What arrow? No need, no
No, no,
need.
no.
Cancel diagram, no need.
Like this.
Okay. Say what?
No need.
Say how you draw the line. Say why you draw the line.
Ah.
Why you draw the line? Just explain this line, how you draw, why you draw. There must be a reason.
Oh, because it's like a subset.
You say. Say.
Hey, so like, do you guys know the reason why I put these lines?
Yes.
Okay, good.
No. Say. Yeah, please explain that. Explain.
Okay. So the lower part, okay, each of this lower part is actually the subset of the one from the upper part. So it's like this, people. Okay, understand, right? The answer.
Understand? Okay. Okay, good. Thank you. So yeah. So because this 1, 2, 3 here contain all the set, so we will place it at the top. Then by transitivity, then empty set is in the set of containing 3 elements, the whole set. Okay. So you don't put the arrows because we know that the arrows is always going up. And we because we arrange the lowest guy at the bottom. Okay, so from here you can see the idea of top and bottom, right? So let's define some new terminology here. So how we describe the diagram we have. So for example, we will call an element maximal. Okay. So at the element in the Poset is called maximal if there's no other element that is greater than it. Okay. So similarly, an element is minimal if there's no element that's less than it. Okay. And from the maximum minimum, we can pick the greatest or the least one sometimes. Okay. So what do I mean by the greatest element? So if A is a greater element, okay, it's called the greatest element. That means everything else is smaller than it. Okay. And similarly, you can define the least one, okay, where you just change the arrow. So an element A is called the least element if A is less than equal to B for all B is X. Okay. So let's look at this example here. So what are the maximum element? So every other thing is less than it. So for example, what's the maximum one? Okay, maximum one is nothing that is greater than it. Okay, what is the maximum element? Okay, nothing greater than it. So for example, this one, right? Nothing greater than it. Okay, maximum. B, which are nothing greater than it for B. What is nothing greater than it? So maximum element normally is the top guy. Okay, nothing greater than it. Okay. How about C? Is the D. Nothing greater than it. D, nothing greater than it. Okay. So how about the minimum one? Okay. So minimum one is the nothing smaller than it. Right. So nothing smaller than it. Or nothing smaller than it. Nothing smaller than it. And then nothing smaller. So this is the minimum. Okay. So out of these, so what are the any greatest element in A? Okay, no. So there are no greatest element. Okay. Okay. Why? Because B and C are not comparable. Okay. B, C, D are not comparable. So we don't know which one is the greatest one. To be the greatest one, you need to be greater than all of these, all of the others. Okay. How about smallest one? Does graph A have the smallest one? Yes. Okay. So A is the least element. Okay. How about B? Do you have greatest and least element? No. No greatest or least element. Okay. Because you cannot compare D and E. You also cannot compare L and B. So you don't know which one is the greatest or low. C, least. E. Do you have greatest element? Who is the greatest one? Huh? What? D. Again. D is the greatest. How about lowest least element? No, right? Because A and B is not comparable. How about D? D is the greatest element. And then A is the least element. Okay. The least element. Okay. So greatest because everything is less than D. Everything is greater than A. So it's a least. Okay. Yeah. Okay, last part here. Last part for the section. This one. Wait first. Okay, so just now we look at the whole Poset, right? Now we can look at the subset of Poset. Okay, we can just look at subset of it. Suppose you have a subset of Poset. Okay, subset of Poset. Then we can look at a similar concept which we call an upper bound for a subset. Okay. So what's the upper bound? So upper bound is an element of X such that it is greater than A for all the elements in the subset. Okay, this is called upper bound. So you can bound everything in your subset. This is upper bound. And a lower bound is the number, is the element that can bound from the bottom. okay, which is less than equal to all the element. Okay, lower bound. Bound from bottom, and then upper bound bound from the top. So among all the upper bound, so you can keep imagining you going up, keep going up. Then you can find the smallest one. So you come down and found the smallest one, the least upper bound. Okay. The smallest one among all the bound. So what's the least upper bound? So maybe I highlight the word. So the least upper bound, first you need to be a upper bound first. Okay. It's the element A. If for every A in your set, A is less than the upper bound, and X is less than or equal to all other upper bound. Okay, so this is the least upper bound. Okay, and then similarly, we have a greatest lower bound. Okay, so you could imagine the lower bound can go bottom, go to extremely bottom, but we can find the greatest one. Okay, if it is a lower bound, and it is greater than all the lower bound. Okay, so let's look at some example here. So we have this another poset here. So let's look at a subset A, B, C. Okay. So the question is, what are the upper bound? So what's the element that's greater than A, B, and C? Okay. So what are the elements greater than A, B, and C? What do you think? What are the elements that are greater and equal to A, B, and C? Huh? So you got E. What else do you have? Right? But D. So is D an upper bound? So D is greater than B, which is greater than A. Okay. But is D greater than C? No, because there's no line connecting B and C. Okay. So D is not. F. Okay. Why F? Because F is greater than B, greater than A, greater than C. Okay, so D is. What else? J. Huh? Did I write something wrong? This one is F. Huh? Yeah, J, and then H. H can or not? Yeah, H can. H can. H can. Can. Yeah. Okay. Anything else? That's all I think. Okay. Yeah. G cannot because G got no connection to C. Okay. How about lower bound? Huh? What's the lower bound? A. Okay. And I think that's all. Only A only. Okay. So what is the lowest upper bound? LUB. Among the upper bound, which one is the lowest one? E. E. Okay, because E is less than everyone else. Okay, so E. How about upper lower bound? Greatest lower bound. A, because only one A only. Okay, so let's try another example. Try another example. So let's try this example then. BDG. Okay, BDG. Okay, pick the subset. What is the upper bound of BDG? BDG, where is BDG? BDG here. What are the upper bound? H. Okay. Anything else? G. G. So G is greater than G, greater equal G, and greater equal D, greater equal D. So G is in here. I think that's all. How about lower bound? What do you have? A. Yeah, right. B. Anything else? No. Okay. Because on the line here. Okay. So which one is the GLUB lowest? Lowest is it? No, least upper bound. What is the least upper bound? G. Yeah. G is the least upper bound. How about greatest lower bound? B. Okay. So G. L. Okay. So exercise, you can go work out, try different set. Try exercise. Try find for the set JH and ACDF. Okay, you can go and try ACDF and JH. Okay. So after we learn all these, right, finding upper bounds and lower bound, we can define a thing called lattice. Okay. Lattice. So partially ordered set, a poset, where every pair of elements you can find the least upper bound and the greatest lower bound is called a lattice. Okay. So I'm not sure, but lattice, at least to me, is something like this, right? Lattice. Okay. So actually, this lattice will fit into this definition here. Okay. So it's a poset where every 2 points got a upper bound and lower bound. Okay. So in your textbook, they gave 3 examples here. 2 of them are lattice, and then 1 of them is not. Okay. The one that's not a lattice is this one. Okay. So if it is not a lattice, that means that there's one pair that doesn't have least upper bound or greatest lower bound. Okay. So that means you need to find a pair such that you can't find the least upper bound or the greatest lower bound. So if you look at BC here, okay, BC. So you try to find the greatest upper bound, least upper bound. So what are the upper bound here? It's D, E, and F, right? Because these are greater than these 2. Okay. So what's the least one? You need to choose between D and E. Okay. But D and E are not comparable. So we don't know which one is the least one. So there's no least upper bound here. It has the greatest lower bound, which is A. Yeah. But there's no least upper bound. Similarly, for this, you should pick any 2 and then try to find a least upper bound and the greatest upper bound. But for all these, you can find at least found 1. So they are all letters. So A and B are letters. So maybe try verify. Try verify that A this is okay. Yeah. We will start at lattice, and lattice will be the first step before we step into the next topic. The next topic will be on graph and trees, and it's a long topic. We'll spend like 3 weeks on graph and trees. It's a generalization of this lattice. Okay. Yeah, any question on the previous part? Any question before we go into break? And then if not, we will break until 11:02, and we'll come back for the corner.
我同学跟我签了，我以为他哪天还帮他们签。
是的。我说什么事？这3个是什么？
他们当时传到他们那时候，他们帮我签了，然后我以为传到我这时候，我看这都没签，我以为他们也忘了，就帮他们补上了。
哪里？
涂出来了。
哦，OK，
就那个。
这是下周的。OK。
我觉得这里有点乱，就是那个 decimal 是，它是直接比它小嘛，就是说只要没有比它大的，它就是 decimal。
没有比它大就是没什么。对。
greater 是就是看关系，所有的绝对关系的都是它的下层，那它就是 greater。
再说一次。greatest 的话就是，如果是 greatest 哪一个？有2个 greatest 对吗？
这个跟 decimal 一起。
哦，OK。这个 greatest 的话，它是大于所有里面的。
就是处在顶层。
啊，对，只有一个可以处在顶层。看一下。呀，有2个处在顶层，你就不能够比较他们。
但他们都是 decimal。
啊，但是只有一个存在的话，它就是greatest。这只可以是一个嘛？
那我就看整数，如果第一层是多个，那他们都是 decimal；如果就一个，那就是。然后这边这个 greater 是可以包括他们的数的，如果3个都在一旁边，就可以就是可以包括他们自己。
对，因为自己和自己也有关系。
是的。最后这个我看就是哈斯
还是
对，他是不是去掉这个或者直接什么吧，就不需要这个。
可以是去掉。
就 remove 那个。
对 ，remove 那个 loop，remove 那个多余的 sensitive 的 edges， 然后去掉箭头。
那怎么变成
这个哈，就是他可能一开始的时候，
开始这边有调了另一个名字。
什么东西？哦，我要看一下 Poset 是这个啊，这个是 Poset。
对，就是整出。
这是你自己画的还是？
看就自己找了个例子，因为
OK，
第一遍看上课那例子不太懂。
OK，等一下啊，我看一下啊，这是3啊，这是3。
3对。其实这些我都懂，但是最后为什么要讲这样？然后他
因为这是简化的，所以你这一个图是不是？我看一下，讲一下啊。 OK， 所以我想说这个图呢，你说怎么把这个变成这个？
对，就是我去除了一些图形后，我整理成这样的规则。
我觉得你应该把比较少箭头的放在，就是越少箭头，你就把它放在越低的那个层次。OK，
就越少箭头指向它的就是越低的。
对，因为为什么？因为很多箭头，意思说多余的那个箭头可以透过其他人到达。
嗯，
所以最少箭头你放在
最底层。
最底层，然后你这样排上去过后，然后你再把多余的这种多余的箭头把它去掉，就剩下最基本的箭头。对，明白。对，这个箭头的错。
哦，是吧？
对，谢谢。你把最少箭头放在最底层，比如说你把这两个放在最底层，然后上一层是什么？
上层，这样子。哦，对，应该6，然后12、36、24、36、24、25、谢谢。
如果你想要做实验，不是，你是从这个开始，然后试下把多余的箭头丢掉，比如说这一条，因为你可以用，哪一条？比如说我想想，比如说这一条可以丢掉，因为2可以去6，6可以去10。你试下丢完它，然后你再用你的箭头跟指向把它从低往上排，也是会到的。
但是丢完的话，它不是就是没有那个这是那个传递性的
transitive
这个不就没了，会少一些箭头。
把 transitive 的箭头丢掉，但是你会有这个基本的箭头在。就是把2到12的丢掉，因为2还可以去到6，6还可以掉成。
那就是直接按箭头排，然后它那个多少？
对，也可以试一下这个版本。
我们那个其他的都是扣的比较。
你是说你的？可能有些有些答案错吧，对不对？但是你有一些东西写到有点乱，所以我没看清楚。然后我回去再看一下，好像写的还可以，所以我后来加了一些。
也提前签了，
说他签错去，他说，怎么还有人可以去玩的这样开心呢？
好玩是啊，昨天，然后下一个礼拜2个，其他就是去玩了。
那你们2科考试还是去玩？
这个因为就是那样5天嘛，现在全部讨论要去玩了。
怎么在同一天？考试在同一天啊？
下个拜四了，
然
后加上老师你的 quiz，本来他们没这压力，可能就加一个 quiz，可能就现在先玩嘛。
这么爽
4、6日，拜1、拜2，6天嘛，尽力了。这里有测验那种，对吧？那个昨天也是有中国的朋友嘛，就问我，真的去哪里好玩？
去云顶哦。
有时候我是可以去，不过这段时间是云顶会比较危险，为什么呢？下雨很多嘛。很多 accident 就是雨季，然后 发生的，不是？
对对。
而且云顶好像也没有以前这样子嘛，不是？我不懂这个是反正也没700个啊。感觉是以前去比较像事情，像事情。
好的，OK，you can start do the tutorial questions. There's a lot of equivalence relation in the question, which you can try practice to show the reflexivity, transitivity, symmetry, okay? Relation. Try the relation. Try to show the relation. 看了，看了看。
那这样会做吗？那个考完了。
那你最后一题，那最后一题可以教过，最后一题是差不多3。
那就不能啊，对，all n 我们也可以讲过。这个，这样这样代码怎么改？我们教你，帮我写代码，那啥上的方式，好上的，上的，代码，这样子，跟我们搭上的时候，数字里面算推断算吗？推导，也不是推导，就是要算，还没有到推导，是在算嘛。这得考验自己之后，考验自己就是要先把那个口给了给。
我年轻的时候，在看他们 就是只要你，比如说你，比如说这个里面，现在力学，在他的想法里面，他只会懂非常他在学他的成分吧，就是一个档级，先学打量这个，出现在别人是我们的特点，变成了。对对，他也是有可能，可是他。是就记得他的位置的，然后是学着去变他的课程。就不傻了，完全完全。
那天解释出来，就是因为这个老师说这个 project 太难了，每个人他就简单化原理来讲，后面讲的啊，这个的认真基本跟那个就是要实际化这个。我想最简单的是太方便。多少个人？我这个报告表的记录。他们的报告量也是，报告就没有量，这个怎么说明的？我还要去说的这点吗？不用拍，就是。
我们的管制到在那边，高度在高，如果还有个 C，symmetric 会是两个 A 在 B 的方面上，这个 B 的 A， 这个应该也是好的，
不是 reflexive。
是应该的，自己的他肩膀的好像也行。A 有这个情况也是一个人的 symmetry 是指，symmetry 是说如果A B B A 那 A 怎么那个 B 也对吧？这里 B 跟 A 有对吧 ？B 也有对吧？但是 A 你就想它是这样扫在，然后 A 扫在 B 扫在 A 就可以发出 A 的 A， 所以就等于。就是说，你不要看它两个修的意思，对 B 啊。B 都是在 A B 相反 A B 那是 A B 就 A B 和 B A 搞出来 A 等于 B， 也就是两个字的折合是好像把 G B 三个有 A B 和 B A 能得出来 A B， 这就是换成通俗的一个哎，我知道，有一个安贴就是你说拿大于等于就是关系吧。比如说 A 大于 B，A 和 B 大于 B， 当这个在 A 大于 B 那个他也是在生日啊，而且他也是大个 B 的结婚，那生日能和他自己看吗？那个是 dyslexic， 对啊，我跟你朋友在哪里高？这是个例子，除了第一个啊，第一个是我们得刚刚那个是哪一个 A C 第三个这啥应该要3的吧？应该要那个，它是什么性质 ？A 是它的对 A 是A 是什么地方？那是一个。大于 B 的话 ，B 就肯定是大于，所以它在这个体系，它是不可能的。不可能大于 B 大于 B， 因为它是前提，可以按这个比较，因为它不存在这个，所以它现在证明是可以。但没有大于 B， 也没有没有。这个答案找不出来就不可能。你可以找出里面有详细的。 因为他没有这个管理层的问题。比如说你说一个空子，它其实这个性质不好，还是一个例子。除了那个。除了之前其他的是没有，除了来没有。原来给我带个，我跟你讲，淘宝买的真贵，淘宝不好，不贵啊，如果又便宜，没有的贵，它讲不贵，贵，运费。因为加价，你说买得了，还是便宜，我跟你讲，我那个真的有好贵，那个真好贵。就是中国上快事我从来不想买那什么报修水漏不会，什么银行卡不会，什么买东西不会，问路会点会一点啊，你要加叫 Grab 会 Grab 我大部分用 cash 不要 Red Pay， 用 cash Red Pay。我在要那个保险，不是那个阿凡达2，这个是黑豹。黑豹，他们说啊，黑豹，你看，没见过。机会到了，你有吗？给发奖他干嘛？他又不是要坐飞机的那种。坐车就可以到，而且那个蹭的还是跟你 QQ 啊，蹭走的钱，要求在啊，找我人呢？就没有别的，这就是哦，就这样。何鬼？就是而且用这笔记本这么，老师 iPad 这么大，它这是12寸的，原来它有吗？我一直觉得为什么它的特别大，真的，跟小孩似的，那个，这12.9的好像。其实不上课，咱走吧，你不会参与吗？没反应，直接写个帅飞，你写个 offer 就帅，那个有的意思，对吧？我刚写，他有意思，你看，哪个做的？啊，还是广告往上滑。这都前8了，还有13 Pro Max， 还是有点距离了，还是有点距离。你现在新加坡怎么样？有没有把新加坡都红啊？你到底是新加坡的人？都看我的人，我好算了。是，就1000多。
多少类型？
大家反正颜色是有不同的那种，好像没有吧？也是没有，都有这一代的。我看了，我们这些人因为规定涉及到这个啊，
Hello. Okay. There's a lot of equivalence relation questions, so you have to try all of them. I'll put out the answer today because tomorrow I don't have class. Who go back for voting? Election voting. Who else? Who else going back to election voting? Okay, very good. Please go home, vote for a better Malaysia. Okay.